Well, hello all, my name is Stephen Thomas, and today we're going to be dealing with one of my absolutely most favorite reactions. Let me show you it. So what do we have here? We have our Sodastream, and inside it, it's got a canister of carbon dioxide. You buy these canisters. This one says 21 Rand. It's a very old canister now. They cost 121 Rand. So what a Sodastream requires is you take a bottle of, this is cold, plain tap water. You screw it in. Once it's nice and tight, you press the top button. It injects carbon dioxide into our water, and now we leave it for a minute or two so that the carbon dioxide can dissolve in the water. So let's leave it for a while. It's best to use cold water because surprisingly gases dissolve better and stay longer in cold. You can see this is frosty. They stay better in cold water. I think hot water, the molecules are vibrating according to the kinetic theory, and they shake the carbon dioxide out of the water very quickly, and the oxygen, all gases in fact, which is strange because sugar dissolves better in, solids dissolve better in hot water, but gases dissolve and stay in better in ice cold water. So we have to leave this for long enough so that the carbon dioxide can dissolve, get into and dissolve in the water. Did you see how this sprays lots of little bubbles into the water? It's better, with lots of tiny little bubbles, it can get to the water molecules and spreads out throughout the whole bottle. And so here we now have our soda bottle full of carbon dioxide. You can see when I release it, it releases some of the pressure. Do you see how you're starting to get bubbles coming out? There were no bubbles before, but now you can see the bubbles are beginning to come out of the solution. So to stop that, we put the top on, and that will stop the bubbles suddenly coming out. But this was clear beforehand. There were no bubbles visible. If we shook it, the bubbles would come out even faster. Now the section we're dealing with is this section called Chemical Equilibrium and Factors Affecting Equilibrium. Explain what is meant by an open and a closed system, a reversible reaction, a dynamic equilibrium. So that we're doing number 88. List the factors which influence the position of the equilibrium. So what is meant by equilibrium? And what is, first of all, an open and a closed system? Well, if this is our Sodastream bottle, if we open the bottle and things can exit, like gases can come in or go out, if we can put carbon dioxide in, or if it's allowed to go out, this is an open system. But the moment we close the bottle, we have a closed system. So reactants and products, anything in this bottle cannot get out of the bottle. That is the difference between an open and a closed system. So what reaction took place when we had carbonic acid, when we put carbon dioxide, we Sodastreamed water? Let's have a look at the reaction. And this, as I say, is one of my favorite reactions, or at least it's one of them that I use most often. We've got CO2. That is what came in this Sodastream bottle, right? So here was the carbon dioxide. Then we had water in this bottle. All it was pure tap water. So that's what we started with. We had nothing else. And then it went to form H2CO3, or anything with H. Sounds like it's an acid, and CO3, carbonate, carbonic acid. Hydrogen carbonate, I guess you could call it.
So here is, and is it balanced? Well, let's count it. One carbon, two hydrogens, two hydrogens, one oxygen plus two oxygens, three oxygens, three oxygens. So our reaction is balanced. We always work with balanced reactions. But now these things here at the start were our reactants. And then these things that we ended up with were our products. Now at first we only had reactants, carbon dioxide and water. And then at the end we had products. But this is a new type of reaction for some people. Did the water completely disappear? Of course not. There's still water in this bottle. There's still CO2 in the bottle. In fact, if you look at the bottle, you can see the bubbles of CO2 in the bottle and you can see the water. But there must be also a little bit of carbonic acid in our bottle. So this is the wonderful reaction that if you pump CO2 into water, the CO2 actually, there's a chemical reaction. Carbon dioxide and water combine to form carbonic acid, which is a completely new chemical. Now, actually it doesn't produce that much carbonic acid. But the carbonic acid can reversibly go to form water and CO2. And you see that particularly when you open the lid. So this reaction can go backwards as well as forwards. So this is what we call a reversible equilibrium. Now, if we've got a certain concentration of that, and a certain concentration of that, and a certain concentration of that, they are called being in dynamic equilibrium when their concentrations cease to change. Now have a look at this. At first, we've only got CO2 and H2O. When we start to pump the CO2 into the water, there is no carbonic acid. So the concentration of that is 0. The concentration of that is high. Concentration, well, water's got there is no particular, you can't talk about a concentration of a liquid. A liquid is a liquid. It's got a uniform concentration. But our CO2 gas, I guess we could even write here that it's a gas. This is a liquid. And this is aqueous. So that would be the subscript. A gas plus a liquid goes to form a solution, an aqueous solution. So at first we've got a high concentration of CO2. It dissolves in the water and it produces carbonic acid. Now, obviously, not all the water turns to carbonic acid. So we've got a certain concentration of carbonic acid in the water at the end. Now, once the forward reaction, this plus that goes to form that, is equal to the reverse reaction, which normally happens after you leave it for a few minutes, at the moment it's in equilibrium. You're not getting any more carbonic acid formed. You're not getting any more CO2 formed because it's under pressure here. The carbon dioxide cannot come out of the water because this is a closed system, a closed container, and when there's enough pressure pushing back down on the water, the CO2 bubbles can't escape. So that's why you need a closed system. If we open the bottle, what would happen is the following. If we open the bottle, you're going to find that the reverse reaction becomes greater than the forward reaction. And so now we're going to get the carbonic acid is going to go back to forming CO2, and we're going to get the fizz coming out of our glass. So you're going to see CO2 and bubbles continually coming out. Why? Because it's no longer in dynamic equilibrium, because now one reaction, the reverse reaction, carbonic acid, is reversing and it's forming CO2 gas bubbles. So in the bottle, when it's sealed, we have an equilibrium where carbon dioxide and water is going to form carbonic acid, and carbonic acid is reversibly going to form CO2 and water. And when the forward reaction is equal to the reverse reaction, we say it's in dynamic equilibrium. And we can change that equilibrium by taking the cap off the bottle. Let's change that equilibrium. We take the cap off the bottle, and now you will see bubbles of CO2 start to come out of solution. Now it's bubbling much more freely than it was before. There's lots of bubbles coming out of the solution. So now we can actually see the reversible reaction as the bubbles come out of the solution. Carbonic acid is changing to, let's wipe that clear. Carbonic acid is changing to CO2, and that's why you see those bubbles coming out of the solution. That is the reverse reaction. Now, how can we get a new equilibrium? If we close it again, we now have a closed system instead of an open system. Now it's going to build up pressure. The reverse reaction is going to get smaller and smaller. So let's delete that, till eventually we're left with, again, a new equilibrium where the forward and reverse reaction rates are the same. We always talk about the reaction rate. The rate at which this goes to form that is the same as the rate that this goes to form the reverse. The product's rate to form reactants is the same as the reactant's rate to form products. So now we reach equilibrium again when both rates are the same. It's not that CO2 and H2O never stop forming carbonic acid, or that carbonic acid doesn't go back to form water and CO2, but the rates at which they're going are the same in both directions. And that is what we call dynamic equilibrium. So let's just go back to our syllabus. Yes, we've explained what's open system, where things can come out in and out. Closed system, where nothing can come in or out. What's a reversible reaction, and what is meant by dynamic equilibrium, and then the factors that influence the position of the equilibrium. I'm going to go to Mimi. Okay, physical sciences, quanta. Mimi Pretorius. Let's just have a look what she says about this. I like her summary notes. Equilibrium is reached in a closed system when the rate of the forward reaction equals the rate of the reverse reaction. It is called dynamic equilibrium because the reactions do not stop when equilibrium is reached, but continues at equal rates. You see, we talk rates, the amount per time. It is called equilibrium because rates of the forward and reverse reactions are equal. So the forward reaction is the one to the right, the reverse reaction is the one to the left. Equilibrium is reached when no visible changes can be observed. So when we have our bottle of soda water, you can't see it changing. You don't see any more or less bubbles forming. When no visible macroscopic change can be observed, e.g. the pressure, color, temperature, concentration, and volumes do not change any longer. Equilibrium can only be reached in a closed system. Now here's her definition. A closed system is a system in which all the reactants or reagents and products remain in contact. No mass is transferred into or out of the system. We can't put more carbon dioxide or less carbon dioxide. E.g. a gas is not allowed to escape or enter, or a precipitate is not formed that sinks out of the solution, etc. So there's no solid forming in the solution. In an open system, the reaction will run to completion until one of the reactants is used up. So if we were to open the bottle and leave it open, after time, all your CO2 would escape and all you would be left again with would be water. Then a homogeneous equilibrium is equilibrium in which all the reactants and products are in the same phase, and in a heterogeneous or heterogeneous equilibrium, the reactants and all products are in different phases. So apart from the bubbles would be gas and the water would be liquid. So if you can see it, then it's heterogeneous, but let's suppose you couldn't see it, you'd left it for a long period of time, there were no bubbles, it just looked like clear water, that would be a homogeneous equilibrium. Then here are the factors affecting equilibrium. If a system is in equilibrium and any one of the following is changed, the equilibrium can be affected. Temperature, pressure, concentration. Now, do you remember which one we changed? When we opened the cap, or at first we changed the pressure, and the pressure forced the gas in. But when we let it go, we're changing the pressure again. A catalyst does not disturb equilibrium. It only causes equilibrium to be reached faster. Remember that temperature, pressure, and concentration are factors which affect equilibrium, but not a catalyst. In order to predict how the equilibrium is affected by any one of these changes, we use Le Chatelier's principle, which says when the equilibrium of a closed system is disturbed, the system reacts in such a way as to oppose the disturbing factor to again reach equilibrium. So if we have a closed system, we have our bottle, and I open the cap, I'm changing the pressure. Now there's no pressure. There used to be a high pressure in this bottle. And we close it again, we're going to find that it's going to go from carbonic acid to carbon dioxide until the pressure is restored in the bottle. So it is going to, the reverse reaction is going to occur. It's going to go from carbonic acid to CO2 until the CO2 pressure builds up again, and then no more carbonic acid will go to form CO2. So that is Le Chatelier. If you open this bottle, CO2 will come out, start coming out. That's the reverse reaction. So if we close the bottle, it will continue with the reverse reaction until the pressure builds up again, and when the pressure builds up, it again reaches equilibrium, a dynamic equilibrium. So that is Le Chatelier. We disturbed it, we removed CO2 from the closed system, and then it had to go and produce CO2 again. So if pressure is increased, the system tries to decrease pressure by favoring the reaction shifting to the side that produces less gas molecules. So in our case, we reduced the pressure, so the system tried to increase the pressure by the reverse reaction. If temperature is increased, the system tries to decrease the temperature by favoring the endothermic or energy-using reaction. If the concentration of any substance is increased, the system tries to decrease that concentration by favoring the reaction that uses that substance. So if we increase the concentration of CO2 gas, well, that's pressure. But the CO2 that's dissolved in the water will, now that it's dissolved, will go to form carbonic acid. So that's the forward reaction. So if there's pressure, if we give it a boost of carbonic acid, it will try and get rid of it by using the forward reaction. Whenever you answer a question where you apply Le Chatelier's principle, make sure that you answer the question exactly what has been asked. Does the question ask the shift of equilibrium, or the change in rate, or the effect on the yield, or the change in the color? Okay, so what they're saying is read the question. The principle is applied on the disturbing factor and not on the effect of the disturbing factor. E.g., when the pressure of a system containing gases is increased, or in our case decreased, then you should apply Le Chatelier's principle to the change in the pressure only, and not to the change in the temperature due to the change in the pressure. So we've only talked about what happens if you change the pressure of this bottle. So don't start talking about temperature then. One cannot change the temperature or pressure of the reagents or reactants or on the product separately, because in a closed container both the product and the reagents are mixed. So you can't change the temperature of the left side or the right side separately. You have to change both of them. You cannot change the temperature of the carbonic acid without changing the temperature of the water and the gas in this closed system. And then we come next time to a thing called the equilibrium constant. But that's enough for this particular video.